Good afternoon, everyone. So today is lecture number 20 of this heat treatment class, and today's topic is basically on stainless steels. Because the motivation to the topic is here we'll discuss about some heat treatments, basically, or what is the significance of heat treatment in this, and uh, and some problems which we can face during our heat treatment of this stainless steels. So basically, we know that stainless steels is those category of steels which do not show discoloration. Basically, the color will not change with time because of this high percentage of chromium, right? Or this is stain free because you understand the percentage of chromium is so high, which increases the resistance to the corrosion, basically. Or we can say it also provides high oxidation resistance. If the temperature is also high in the service condition, it will not corrode easily or it will not get oxidized. Right? Due to this formation of this chromium oxide layer on the top of the steel, it prevents the corrosion or oxidation. And you can see these steels are somewhat expensive, obviously, because due to these alloying additions like chromium, nickel, and some alloying additions like molybdenum, aluminum, and all, right? So these steel are somewhat expensive compared to that of normal carbon steels. This stainless steels comes under basically high alloy steels or medium alloy steels. And you can see the basic types we have on stainless steels are, we can categorize the stainless steel into 4 categories. Some people also classify into 5 categories. So basically we have this ferritic stainless steel, austenitic stainless steels, martensitic stainless steels, and precipitation hardenable stainless steels. So these you understand, since we are talking about this ferritic, martensitic, austenitic, precipitation hardenable stainless steels, you can understand that the basis of the classification is their microstructure, right? What kind of microstructure is there in that particular steels? Or you can understand, otherwise you can say the what is the matrix microstructure, right? That decide which kind of steel it is. And if you can remember in the previous lecture which we have discussed, that is there are certain alloying elements which we call ferritic stabilizer, and another one is austenitic stabilizers, right? So those are some specific alloying elements which stabilizes the ferrite. That means it is destabilizing the austenite region. And there are certain kind of alloying elements which stabilize the austenite and which destabilize the ferrite, right? And if you remember, there are certain exception where the alloying element crystal structure is different to that of ferrite, and there are certain alloying elements whose crystal structure is different to that of austenite. For example, if uh, in common statement, I can say that ferritic stabilizer are those alloying elements which are basically having BCC crystal structure, but it's not always true. But specifically, it is not always true, right? The best example I can give you is silicon. Silicon is a ferritic stabilizer which is of diamond cubic crystal structure. And and the interesting point is aluminium. Aluminium is FCC, but it stabilizes ferrite. But I don't know exact reason behind that. But still, you have to remember. This question may be asked that aluminium is a ferritic stabilizer or austenitic stabilizer, but the answer it is a ferritic stabilizer, even if the crystal structure of aluminium is FCC, right? The ferrite is BCC. And another point, some exception in case of austenitic stabilizer like cobalt. Cobalt is a austenitic stabilizer. The cobalt crystal structure is HCP basically, up to like 440 degrees centigrade. But above 440, like 450, it is again become FCC. That means cobalt showing allotropic modification. So cobalt is an exception where it is HCP, but it stabilizes the austenite phase. And if other examples, let me remember, silicon, aluminum. Okay, fine. These are some exceptions. And if you remember, the carbon and nitrogen, these are non-metals. You understand? These are non-metals, but this carbon and nitrogen basically stabilize the austenite phase. Okay, fine. So here you can see a question is there. Okay, fine. If you talk about the cost of these stainless steels, you can understand martensitic steels, stainless steels are somewhat cheaper. Hmm. But if you look into the ferritic stainless steel and these precipitation hardenable stainless steels and austenitic stainless steels, they are expensive because the amount of alloying element is more and different alloying elements are there, right? That's why it is more expensive. But the cheaper one is martensitic stainless steel. And okay, so you understand if I'm talking about ferritic stainless steel and martensitic stainless steel, so basically, these are chromium based stainless steel, right? If you remember, if somebody will ask what is the definition of stainless steel, we can define the steel which contains chromium above 11.5% or basically above 12%. So there is no clear cut definition, but 11.5% is enough to define it. But addition to that, we can have nickel, we can have some other alloying elements. But if a steel contain chromium above 11.5 weight percentage or above 12 weight percentage, it is called stainless steel only, right? Whether it is containing other alloying element, it doesn't matter. So yes, so I'm talking about ferritic stainless steel and martensitic stainless steels. These stainless steels are basically chromium based. Whether the nickel is there or not, it doesn't affect. It is still. But if it is nickel is there, for example, it should be very minimum, right? But if you talk about this austenitic stainless steels, obviously we need an austenite phase. So chromium is there, but addition to that, nickel will be there. So minimum nickel percentage will be like 8 weight percentage nickel. And minimum chromium content is, you can understand, 17% chromium should be there, or 18%. So many people, you people have heard about that 18 is to 8 stainless steel. This is one of the most common stainless steel which have wide variety of applications. So 18 is to 8 stainless steel means 18% chromium is there and 8% nickel is there. The nickel is there because nickel is an austenite stabilizer, right? And austenite is a FCC, right? So that's why nickel is there. And some people classify this stainless steel on the basis of series, like 200 series, 300 series, 400 series. But I'm not going into details of that. But still, if somebody will ask what is this 200 series, 300 series, 400 series, basically this 200 series and 300 series belongs to this austenitic stainless steels. Basically, if 200 series, that means some people write 2xx. 300 series means 3xx. 400 series means 4xx, right? So this 200 series, basically people are saying it is having uh, it contains chromium, nickel, and manganese. I'm not sure, but you should check it otherwise. Uh, then 300 series, people are saying it is chromium, nickel only. And 200 series, 300 series, as I told, belongs to austenitic stainless steel, and 400 series basically belongs to ferritic and martensitic stainless steels. And the best example I can give you, the application area of stainless steel is your kitchen utensils, right? Your kitchen sink, kitchen sink, kitchen utensils, they belongs to basically austenitic stainless steels. They do not, you understand, and because how you can justify their austenitic stainless steel, because just by studying their magnetic behavior, right? Because austenitic stainless steels are basically non-magnetic in nature. They do not attract towards magnet. If you can perform an experiment at your home, you can find out whether they are austenitic or not. You just being a magnet and you can attach to them with this your kitchen utensils or this kitchen sink. They will not get attracted towards the magnet, or magnet will not get attracted towards these steels. So they are basically austenitic stainless steels. So austenitic stainless steels means they are non-magnetic basically. We can call it paramagnetic sometimes, because if you do cold working on it, some magnetic behavior can come again into the steels. And basically, the ferritic stainless steels and martensitic stainless steels are ferromagnetic in behavior. They are strongly attracted to a magnet. Okay, so we'll discuss an important point here: how to strengthen these steels. So, if you remember, in earlier lectures, we have discussed about many strengthening mechanisms and how to strengthen a particular steel or a particular material. So, suppose we have austenitic stainless steel, right? So, once I'm mentioning the steel is austenitic stainless steel, that means the microstructure is austenite, right? That means starting from the room temperature to the melting point, I will have basically austenite phase, right? I do not. So you understand? If I have austenitic, so that means, in other words, in other way, I can say, starting from the uh, solidification temperature to the room temperature, I will have austenite phase only. That means there is no phase transformation is happening here, right? No phase change will be happening. That means austenite will not transform into martensite. In other words, I can say. So that means if I have an austenitic stainless steel, I cannot harden or I cannot strengthen this steel by using heat treatment. So heat treatment is not the solution to harden this. So only solution we can have is work hardening. You can harden this by work hardening, or what is the other name? You can say cold working. By giving a room temperature deformation, you can harden this kind of steel, right? That is basically called strain hardening, right? But similarly, if I have a ferritic stainless steel, how to strengthen this? Again, the same issue comes. Ferritic stainless steel means starting from the room temperature to the melting point, I have ferrite only. The ferrite microstructure will exist. Hmm. Or you can say from the solidification temperature of the steel to the room temperature, I have only ferrite, right? So I'm not getting any kind of austenite here. Hmm. So since austenite phase is absent completely here, so there will be no phase transformation possible, right? So again, I can say ferritic stainless steel cannot be hardened by heat treatment process. Hmm. Or by it cannot be hardened by this transformation strengthening or transformation hardening, right? Because this austenite phase is absent. Only ferrite phase is there. So again, the answer is this one. We can harden or strengthen this ferritic stainless steel by work hardening. So again, next is the martensite stainless steel. Yeah. So I have martensite means you understand. That means obviously if I that means martensite means there is a transformation is already there, right? You can transform this steel, and so this can be hardened by heat treatment. You can give a heat treatment, it can harden the martensite stainless steel. So you people understood how this is related to the uh, related to the heat treatment, and how this is related to your stabilization of austenite and ferrite. Hmm. That means ferritic stainless steel have ferritic stabilizer. Austenitic stainless steel have austenitic stabilizer in high quantity, hmm, or in certain amount which stabilize the austenite. Hmm. Yes. So now the another interesting topic, which is again related to the heat treatment here. The problem with austenitic stainless steel during some heat treatment. So there is a problem which we people face when we are dealing with the austenitic stainless steel during certain heat treatment, right? So obviously you might have a question like why
Hello, sir.
this yes.
Sir, how can we differentiate between martensite and ferritic stainless steel without any microstructure analysis?
Without any, yeah, just you can measure the hardness value, you can perform tensile test. The martensitic stainless steel will be very harder and having high tensile strength, obviously, and the ferritic steel will be soft one, it is more ductile one. It is okay?
Yes, sir.
Yes. Because if you remember, there is a structure property correlation is always existing in our steels, right? If the structure is different, the property will be different. Ferrite is always soft and ductile, right? But martensite is a very hard and very strong phase. Okay, so problem associated with the austenitic stainless steel. So now you understood till now that we are not giving certain heat treatment. Why we are performing any heat treatment to the austenitic stainless steel? Even if you will give some heat treatment, there will be no phase transformation will be there. Austenite will remain even at room temperature, right? So what is the need of this heat treatment, right, to the austenitic stainless steel? Obviously, suppose, see, the point is what austenitic stainless steels are very good quality of steels because they have wide range of applications, even at room temperature, even at high temperature, right? They provide good strength, good oxidation resistance, good corrosion resistance. They have also good toughness, good ductility. So that is a very interesting property the austenitic stainless steel have. Huh? They have strength, they have ductility, they have toughness, they provide high corrosion resistance, they have oxidation resistance. You can use the austenitic stainless steel at below room temperature, at above room temperature, right? Very good property austenitic stainless steel have. But the question is why we are giving certain heat treatments. So already I have written over here. You can see annealing heat treatment is given, stress relieving annealing heat treatment is given. So you understand uh, when we are welding these steels, during the welding, obviously you understand stress will generate. So to relieve those stresses, we are giving stress relieving heat treatment to the austenitic stainless steel. So so that means yes, now you people understood, huh? And yeah, suppose you want to give full annealing heat treatment. So what is the need of giving full annealing heat treatment? You understand the only way to strengthen or to harden a austenitic stainless steel is to deform it. That is cold working, right? So to make the cold working possible, obviously you have to give annealing heat treatment, right? Unless until you will not give annealing heat treatment, you cannot make it cold work, right? Cold working will be not possible. So now the question is what kind of problem will arise when we are doing stress relieving or during annealing heat treatment of these steels? So problem arises is the sensitization. Sensitization problem. So the term is called sensitization in stainless steels. So now we'll fully discuss this. What is sensitization? So you understand this term basically comes due to sensitivity. The term is called due to sensitivity of the steels to a particular temperature range. So that means if we do heat treatment on the steels or we are hitting the steels at this range, if our holding temperature or heating temperature and holding temperature is this much, 425 degrees centigrade to 750 degrees centigrade, this kind of effect is coming into the picture, sensitization. So that means these austenitic stainless steels are more sensitive to this temperature range during heating, during heat treatment, 425 to 870. This figure sometimes vary. This figure sometimes vary. It is not exactly this range. It may be sometimes up to 750 or 800. It varies sometimes, depending on. So now the question is what happens at this temperature? What happens at this temperature will justify what is sensitization is basically. So sensitization basically means you have a austenitic stainless steel and you are taking the austenitic stainless steel to suppose 500 degrees centigrade and you are holding it for some duration of time. So what happens basically? Obviously you understand chromium is there, carbon is there, right? So the chromium will start reacting with carbon and it will form chromium carbide, right? So chromium carbide will form and this chromium carbide will get segregated along the grain boundary, along the prior austenitic grain boundary, right? So you understand that means what will happen? Chromium will start reacting with carbon and it will form in chromium carbides, and this chromium carbide precipitate will form along the grain boundaries or near the grain boundaries area, prior austenitic grain boundaries area, right? So that means some amount of chromium will get depleted near to the near to the grain boundaries, right? From near to the grain boundaries, the matrix of the matrix which is near to the grain boundaries, the chromium will get depleted. The chromium amount will get reduced to a large extent. And we understand chromium is there in the steel to provide resistance to the corrosion, resistance to the oxidations. But now, due to formation of this chromium carbide, the chromium is getting depleted near to the grain boundary area. So once the chromium will get depleted, the corrosion will start, and the temperature is high. The corrosion will start, or oxidation will start. The failure may happen due to this corrosion. So that is called sensitization effect. Right? So you understand what is the consequence of this? The consequence of this is you can write the resistance to the corrosion and oxidation will reduce near the grain boundaries, because due to depletion of chromium from the matrix, which is vicinity to the this prior austenitic grain boundaries, right? The consequences, the failure may happens due to this corrosion. Fine. And now what is the solution? So we can have three solutions to this sensitization. Uh, the first solution we can have is we can reduce the weight percentage of carbon, right? If you can reduce the weight percentage of carbon in stainless steel, austenitic stainless steel, we can protect the steel from this sensitization, right? Because more carbon, more is the formation of chromium carbide, right? So less carbon, so chances of formation of chromium carbide will be less. So this is one of the solution. So I am writing by reducing the weight percentage of carbon, right? I think you people have understood that less carbon means less chromium carbide formation. More carbon means more chromium carbide formations. So we want to suppress the chromium carbide formations. If we want to suppress the chromium carbide formation, we have to reduce the amount of carbon in the austenitic stainless steel. So this is one of the way you can, this is one of the solution we can have. And another solution we can have is we can dissolve this chromium carbide. How we can dissolve? By doing solutionizing heat treatment. Just by taking the steel to a very high temperature where this chromium carbide will get soluble in the matrix phase, that means in the austenite phase, and we have to quench the steel, or we have to do rapid cooling of the steel, so that all the elements will be in the solution state. So by doing solution heat treatment, right? Again, I'm repeating. Suppose already you have chromium carbide, so you can do solutionizing heat treatment on these steels. Solutionizing heat treatment means you have to take this austenitic stainless steel containing chromium carbide to a very high temperature, like 1000 degrees centigrade, 1100 degrees centigrade, where the chromium carbide will get soluble in the matrix phase. Then you have to do quenching of this, or you have to do rapid cooling on this, so that chromium carbide will not form again. It will remain in solution form, right? So this is another solution. And the last solution we can have is by doing stabilization, by stabilizing, by doing stabilizing of the steels. So what exactly stabilizing means? We can stabilize this austenitic stainless steel by just adding some strong carbide formers, right? Strong carbide formers. Best example I can give you tantalum. You can add titanium. You can add columbium, right? So by adding columbium, tantalum, titanium, these are strong carbide formers. So by adding these kind of alloying elements into the stainless steel, austenitic stainless steel, we can suppress the formation of chromium carbide. Chromium carbide will not form, but titanium carbide may form, this columbium carbide may form, this tantalum carbide may form, right? Which will suppress the formation of chromium carbide. So by suppressing the formation of chromium carbide by addition of these kind of strong carbide formers, we can stabilize the austenitic stainless steel. So this is one of the way. These are the three ways by which we can prevent sensitization. So another problem and the issue which we sometimes face, due to formation of some intermetallic phases. Some intermetallic phases like sigma phase. So what happens basically when we heat the steel at a temperature of like 750 to 850 degrees centigrade, a sigma phase, some intermetallic phases which is forming in this kind of steel, which is basically brittle in nature, which is very hard and brittle in nature, and they reduces the impact strength basically. So your impact strength will reduce, and your corrosion resistance will also hampered. So due to formation of these sigma phases or these intermetallic phases in this kind of steels, we our corrosion resistance is reduced and our impact strength is reduced. So this is another problem we can face. Okay, fine. So I'll end the topic here. If you have any questions, you can ask me right here.